In the previous video, we talked about the requirements in order to see a bell-shaped curve coming through for this sampling distribution of. So if we prove that we have a bell-shaped curve, we need to be able to describe the two key components to our bell-shaped curve, which is our mean and our standard deviation. So here, what we want to be able to do is, if we have these x values, which each of these x values are sample means from a population, what we want to see is this bell-shaped curve coming through. So you want to see this distribution of means, and it's where each value underneath this curve here, it's like this is full of x bar values, all those different possible sample means that we could have from our population. So in order to describe this bell-shaped curve, we need to understand where is it spread, because then what we can do is start finding probabilities of seeing certain averages coming through. So our sampling distribution model of means. So the center, as we talked about through the simulation, the means line up with each other. So where this is our average of the sample means, when we average out those sample means, it should just be equal to the population average. So if we're describing how x is distributed, if we meet that central limit theorem, it's going to be normal, so we'll have a bell-shaped curve. And the center for it, this average of the sample means, should just be our population mean. So whatever our population mean, that's the center for the distribution. Then our standard deviation, which here we can see it's a population standard deviation, and then we use that same subscript of x bar, and it's because this is the standard deviation of sample means. Meaning if we have all these sample means in a distribution, if we calculate that standard deviation, this is the notation that we would use for that distribution. So this we calculate, and we calculate it by taking the population standard deviation and divide by the square root of our sample size. So if you remember in that last video, I talked about how sample size will come through because that standard deviation changed based on large sample size versus smaller sample size. Remember, with the larger sample sizes, this thing gets smaller. It's because dividing by a larger number down here. If we have a small number, we're not dividing by that much, so our standard deviation from our population doesn't decrease that much. So the larger this value is for n down here, the smaller overall standard deviation becomes. So for the spread of our graph, we calculate taking our population standard deviation divided by the square root of our sample size. And this is going to give us our distribution of means. So let's go ahead and try this out. In these examples, we're going to be going to our bell-shaped curve and calculating probabilities. And with that, I'm just using GeoGebra with a certain bell-shaped curve and plugging in the values in there. So for this first example, what we're going to work with is population data that is normally distributed. This example we went through in the simulation. So a person's measured glucose level 1 hour after ingesting a sugary drink varies according to the normal distribution. So this wording here is telling us that our population data is normal. And then we have our mean and our standard deviation. So what we want to get at here is, how do we know when to use the sampling distribution of means? So this distribution is describing values for just a single person. Just for one person, how do their levels behave? So in this first question where it's saying if a single glucose measurement is made, define and draw the distribution. Well, if it's just a single value, this is the behavior for single values. So this would not be using the distribution of means. Somewhere, if we're using our distribution of means, it would have to say we took a certain sample size and averaged it. That has to be in the wording somewhere. So here, if x is just a single glucose measurement, Then how it will distribute is they tell us it's normally distributed, so we have a bell-shaped curve, mean of 125, standard deviation of 10. And in terms of drawing our distribution, what that would look like is we'd have a bell-shaped curve. We're at 125, and then we're using a standard deviation of 10. So when we plug it into GeoGebra, this is roughly the distribution we should see. So we want to find what's the probability that a single measurement is greater than 140. So we want to go to 140, which is somewhere in between those two values, and find the probability of it being greater than. So what we want to do is in GeoGebra, mean, standard deviation, and then find the probability of x being more than or equal to 140. And if we plug that into GeoGebra, we should get out a 0.0668. So this tells us there is a 6.68% chance a single glucose measurement, and we could get more descriptive in terms of 1 hour after ingesting a sugary drink, is greater than 140 milligrams per deciliter. So this throws back to our section on just normal distributions. We didn't use our distribution of means here. So when we move to the next question, where it says, if measurements are made on 3 different occasions and the mean result is computed, discuss each of the conditions required to use a sampling distribution of the averages. So here, the key wording is that they're telling us a sample size and telling us that we're looking at the means. And having those work together, that throws to our sampling distribution of means. So here it wants us to discuss the conditions. So it wants that central limit theorem. So for our central limit theorem, we needed independence, which a few ways, so that 10% rule that the book talks about, what we'd be doing is think about our population, which it's not very descriptive, so we could just say it's of all people. So if our population is all people, and we're taking a sample size of 3, because 3 is less than 10% of all people, we have independence. Those are going to be independent results from each other. So that's how we could use the 10% condition, or independence is the idea results should be independent of each other. Their glucose levels aren't affected by each other. So we just need to make a note that glucose levels are independent, and that's all we really need to describe there. Description with these. When you go on to the second course of statistics, you get more descriptive with them, improving these. For us, just quick little check. Randomization. So we should be taking a random sample. So they say 3 different occasions. So these 3 values, it doesn't specifically say that they were randomly collected, but this is where we're going to assume. We're going to assume these researchers know what they're doing and that they are using randomization, because that's the smart way to go about it. So we're going to assume it's random. And we'll just go ahead and say it passes that. What we want to avoid is any wording that clearly shows, like, if measurements are made on 3 friends or something like that, that it's clearly not done randomly. If we fail these conditions, we shouldn't move forward with a bell-shaped curve, because if it's not independent or not random, those values will influence each other and we might not have a perfectly bell-shaped curve like we want. Then our last one is our sample size condition. And with the sample size condition, even though I said the sample size should be more than or equal to 30, and this is a small sample size, remember, if our function is bell-shaped, we're able to draw this curve for our population data, Sample size doesn't really matter. Of course, sample size of 3 is small, so it's small, but our population is normal, so we're actually okay. We meet this condition. It goes. But if our data was skewed here, and we try to use the sample size of 3, we wouldn't want to move, we would fail the central limit theorem, so we wouldn't have a bell-shaped distribution. So, since we passed the central limit theorem, basically this tells us that when we use the sampling distribution of means, we get to use a bell-shaped curve. That's the point of the central limit theorem. So, define the sampling distribution model and its parameters. So, now, if we're taking these averages or these means of 3 different occasions, our variable, what it's going to represent is the average of 3 glucose measurements. And we want to know how these averages of 3, how do those distribute? We know that it's bell-shaped. What we need to understand is how does the average of the means behave? If we have all these averages of 3, where do those center? And this is just always equal to our population mean. So whatever our population mean is, we just copy it down. So when you find this mean of the sampling distribution, no math to be done, just copy down what was given. With our standard deviation though, this is where we need to do a little bit of math, because we take the old standard deviation, so our old standard deviation of 10, that population, and then divide by the square root of our sample size, which in case we're taking a sample size of 3. So our standard deviation is going to be a 5.7735. And eventually we're going to be plugging these into GeoGebra, and it's best to get as many decimal places as you can. Sometimes GeoGebra will just not let you put in the 4th decimal place, so when that happens, just go to 3 decimal places. 3 or 4 decimal places, that gives enough accuracy. Our distribution, if we have these sample means, they're normally distributed because we passed the central limit theorem, centered at 125, standard deviation of this 5.7735. So in terms of a bell-shaped curve, line, we're still centered at 125, but now how the numbers distribute, this would be, and I'm going to round a little bit, 130.7, 136.55, and we get an idea of a number line, and if we compare to the number line up above, we can see happens is we're now much closer to 125. Here we spanned from 105 to 145. Here we only span from 113 to 136. So things have kind of shrunk in, and it's that idea that we're taking averages. So when we take averages, the extreme values out here are less likely to occur. So we kind of focus in around that 125. So this is our distribution of means. So we want to find what's the probability that the mean of 3 measurements is greater than or equal to 140 milligrams per deciliter. So notice here, it's the same question. It's just our wording that's thrown in there is we're looking for the probability that a mean of a certain sample size has these values. So whenever you see probability of a mean, and there's some sample size attached there, we're using a sampling distribution of means. So for this, using our curve, and in GeoGebra, we want to find this area. Ooh, that's not a very good bell-shaped curve. This area above 140. As you can see from our number line here, it's going to be beyond 2 standard deviations away. 140 is somewhere out here, and we want to find this area above. So if we go to GeoGebra and look for this probability of x being over 140, what we should get out is 0.0047. If you rounded this to 3 decimal places, you might get a slightly different number out, but should be close by. What this tells us, now when we make our sentence answers, our description gets a little more complicated. So where our description above here was a % chance of a single glucose measurement, now this is telling us, so there is a 0.47% chance the mean of 3 glucose measurements is greater than or equal to 140 milligrams per deciliter. So what changes is that we're describing an average of a certain sample size. So in your wording, make sure there should be the word mean in there, because we're taking the probability size should be in there. Because our sample size is important to these probabilities, because it's part of the calculation for the standard deviation. If we change this to an average of 5 glucose measurements, our standard deviation would change, which would make probabilities change. So it's important that this probability, this 0.47% chance, attached to this certain sample size. So make sure that sample size comes through in your wording as well. And then what is the 95th percentile for the average of 3 results from this person? So we're looking at a percentile, and we're still looking at averages of 3. So we're using that curve with 125, and then our standard deviation still that 5.7735. And with our curve, this is where we want this lower 95%. So there's some cutoff point, and we want to find what is that X value such that 95% of the data is to the left of it. So in GeoGebra, plugging it in, what we would have is, and remember with GeoGebra we plug in, so X is going to be less than or equal to something, we don't know what, and the area to the left is 0.95, and then GeoGebra will fill in the blank here with the number 134.4966. So what this tells us is the cutoff for the 95th percentile for average of 3 glucose results is 104, and I'm just going to round this to 0.5 milligrams per deciliter. So it's all about finding that new mean and standard deviation for the sampling distribution of means, but in terms of probabilities, we're using the same methods in GeoGebra, it's just the standard deviation and mean came up from a specific spot.